In this video, we're going to look at some geometric applications of the cross product. And to kind of start us along this road, we're going to look and verify the following theorem. All right, so this theorem is going to say the following. So if theta is the smaller angle between vectors u and v, and this has to be in R3 since we're talking about the cross product, then the magnitude of the cross product, u cross v, right, is equal to the magnitude of u times the magnitude of v times the sine of theta. Now this is interesting because if I take the right side of this equation and I replace the sine with a cosine of theta, then we actually get the dot product. Right, so the dot product is associated with the cosine of the angle between the two vectors. But here we have, if we want the sine of the angle, we actually want the magnitude of the cross product. So we can actually kind of do similar things with the angle between using this cross product, but typically we use the dot product because it's much easier to compute the dot product of two vectors than it is to compute the cross product. Okay. Now with the corresponding fact with dot products and cosine of theta, we were able to really quickly see that two vectors were going to be orthogonal if the dot product was equal to 0. And that was because if two vectors are orthogonal, the angle between them is pi over 2 radians or 90 degrees, and the cosine of that angle is 0. In this case, the right-hand side of this equation that involves sine of theta, this will be 0 when the angle between the two vectors is equal to 0. In other words, when these vectors are pointing in the same direction. Right? And so when two vectors are in the same direction, we say that they are parallel. So as a sort of a natural corollary to this, we have that u and v are parallel if and only if u cross v is equal to 0. Okay? So if we want to show two vectors are parallel, this is one way to do it, is to show that their cross product is equal to 0. Right, and this follows from the theorem pretty quickly. If the u and v are parallel, then the sine of theta, the angle between them, would be 0. So if the right-hand side of this equation in the theorem is 0, the left-hand side of the equation must also be 0. So the cross product has a magnitude of 0, and therefore must be the 0 vector itself, since every other vector has a positive length. Right? And we can work backwards as well. If a vector is 0, then its magnitude is 0. The only way the right-hand side of this equation is 0 is when sine of theta is equal to 0, and therefore the vectors are parallel. Right? So let's take a few minutes and look at this theorem and sort of see why this fact is true. Right? So what we're going to do is we're going we want to know something about the magnitude of u cross v. So in order to make the magnitude a little bit easier to deal with, because this magnitude is going to be the square root of some really complicated expression. So let's get rid of the square root by let's consider the magnitude squared instead. And so if we do that, what we get is we should get u2 v3 minus u3 v2 squared plus u3 v1 minus u1 v3 squared plus u1 v2 minus u2 v1 squared. Right? So if I take the square root of that right-hand side, that is the magnitude of u cross v. So I have the square to get rid of the square root. So now we're just going to expand out all of these binomials squared. So we're going to get u2 squared v3 squared minus 2 u2 u3 v2 v3 plus u3 squared v2 squared plus u3 squared v1 squared minus 2 u1 u3 v1 v3 plus u1 squared v3 squared plus u1 squared v2 squared minus 2 u1 u2 v1 v2 plus u1 u2 squared v1 squared. All right, so that was fun. So now what we're going to do is make an observation, and this is where, this is not difficult algebra. You can verify it, but we're not going to go through all the steps because it would not be pleasant to do. This is equal to u1 squared plus u2 squared plus u3 squared multiplied by v1 squared plus v2 squared plus v3 squared. All right, so if I'm not completely done with this line yet, but if we would go ahead and distribute all of these out, we would get several of these terms that involve the squares of the different variables. But we need to subtract off some things from this. So what we need to subtract off is u1 v1 plus u2 v2 plus u3 v3 quantity squared. So those three lines of expression there, that simplifies like this. It's not obvious that it does, but if you just compute out what we have and multiply all this out, you will get exactly what we get in the previous three lines. The nice thing about this is we can write this in terms of the vectors u and v. The first quantity in parentheses, the u1 squared plus u2 squared plus u3 squared, that's just the magnitude of u squared. The second set of parentheses, v1 squared plus v2 squared plus v3, this should be actually the v3 squared. That square should be outside of the inside the parenthesis. Sorry about that. So that ends up being the magnitude of v squared. And we subtract off from that the dot product of u and v squared. Right? So we have the magnitudes of u and v squared here. We're going to keep those throughout the rest of this derivation. Nothing's going to happen there. But the dot product, I'm going to use the fact that we know about the dot product, and that is that the dot product is the magnitude of u times the magnitude of v times the cosine of that same angle theta. Right? So we have cosine squared, or magnitude of u, magnitude of v, cosine theta, all of that squared. Right? Right? Well, we can then do the magnitude of u squared, magnitude of v squared, minus the magnitude of u squared, the magnitude of v squared, cosine squared theta. Right, so we can factor out a magnitude of u squared and a magnitude of v squared from this expression. And what's left is 1 minus the cosine squared of theta. And, of course, 1 minus cosine squared of theta is the sine squared of theta. Right. And remember, I'm going to write this over here because it's not on the screen anymore. This was all equal to the magnitude of u cross v squared. Right, so I have the magnitude of u cross v squared equals this number squared. And so because these are all positive numbers, the magnitude of vectors are always positive, and because theta is between 0 and pi, sine of theta is going to be a positive value. So if we take square roots of both sides, we get exactly what we want. We get that the magnitude of u cross v is equal to the magnitude of u, the magnitude of v, times the sine of theta. Right, so this property can help us determine if lines are parallel. It can also help us if we wanted to, if we knew the cross product, we could find the angle between the vectors in R3 by taking the inverse sine of the magnitude of the cross product over the product of the magnitudes of the vectors. But one of the nice applications of this formula comes with finding areas of parallelograms. Right, so let's consider a parallelogram where the sides are given by vectors. Right, now this parallelogram that I'm drawing should be we want to think of this as being in R3. But of course, a parallelogram is a plane figure. So even if it's in three-dimensional space, we can orient ourselves so that the plane that the parallelogram is looking in is flat in front of us. And so we can think of this as a two-dimensional object, even though it is sitting in three space somehow. Right? So let's say that this side length over here is given by the vector u, and this side length here is given by the vector v. And we've sort of I picked the bottom left-hand corner, so I'm really thinking of u as going to the right and v as going up in terms of vectors. But that's okay. We don't really need that in terms of the formula that we're going to use. So in order to come up with the area of this parallelogram, we know the area is going to be base times height. Right, so this is a known fact from elementary school geometry, is the area is going to be the base times the height. Right? Well, the base we know is going to be the magnitude of vector u. Right? So that is going to be our base. Now we don't know the height as written, but what we can do is we could drop an altitude here from the top right corner. That will form a right angle. And if we let this angle between the vectors u and v be theta, then we know exactly what the height of this altitude is. It's going to be the magnitude of v multiplied by sine theta. Right? This is what this is just right triangle trigonometry. And so our base is the magnitude of u. The height of our parallelogram is the magnitude of v times the sine of the angle in between. And so what we notice is that this is the formula that we just derived for the magnitude of the cross product of u and v. And so if we wanted to find the area of a parallelogram in three space, then what we can do is take the cross product of two vectors that define the sides, the corresponding sides of the parallelogram, and take the cross product and then find its magnitude. Right, so for an example, let's say we wanted to find the area of, let's say, a triangle with vertices in three space of the following. So let's say we have P, which is negative 2, 1, 3. Q is 4, negative 3, 1. And R is the point 553. So looking at these 3 points, depending on your memory, you might recognize these points because we've already considered them in a previous example. In the example before, we took these 3 points, we considered the plane that passed through them, and we wanted to find a vector that was perpendicular to all 3. Right? And so we already did that. So I'm just going to cite the previous example. I won't go through all the work here, but of course, if it's just computing a cross product. So we found that PQ cross PR was the vector 8, -14, 52. Right? So notice that if PQ are vertices of a triangle, PQ is one side of the triangle, and PR is another side. Right? And so if I take the magnitude of this cross product, so the magnitude of 8, -14, 52, right? This is square root of 8 squared plus 14 squared plus 52 squared. And this is where we'll go to a calculator because I have no desire to do that by hand. So it looks like this is the square root of 2,964, right? And so this number right here that we just found, this is the area of the parallelogram that goes through these points, right? And so, for example, if I have a kind of a picture here, this is P, Q is over here, and R is here, right? We want the area of this triangle. But notice that we can make a parallelogram. These 3 points define a unique parallelogram. So there'd be a point over here that we don't need to consider. But this number, the square root of 2,964, is the area of this entire parallelogram, PQR, maybe I'll call this S. So this is the area of the parallelogram PQRS. And now by looking at the picture, we see that the area that we want, the area of the triangle, the red triangle, is exactly half of that parallelogram. Right? So the area of the desired triangle, PQR, is 1/2 of this square root value. Right? So it's 1/2 times the square root of 2,964.